In section 2.3, we'll be creating histograms, which is a graphical display of the frequency tables that we made in the last section. In section 2.2, we were dealing with a data set that showed the age where women first won the Best Actress Academy Award. We used that data set to make a frequency table. We broke the data into classes. First class was 21 to 30, then 31 to 40, etc. And then we counted how many numbers fell into each of those classes. So when we create a histogram, we just take that table and we make a graph of it. So each bar represents the frequency of the class. If we look at this bottom one, we can see the classes here. And along the horizontal scale, we either use the class limits or the class boundaries. So here we have class limits on the bottom. So the first one goes from 21 up to the number before this next number, so 21 to 30. This next bar here goes from 31 up to 40, etc. Okay, we can see these numbers up here. These numbers aren't always here. You can see on the top graph they're not, but that shows the frequency of each graph. So vertical scale shows the frequencies, horizontal scale usually shows class limits, but sometimes shows class boundaries like it does in this graph above. When we're asked to make a relative frequency histogram, just keep in mind that anytime we see the word relative, we're talking about percentages. So these numbers that had been the frequencies just switched to percentages. This graph is going to look exactly the same as the graph on the previous slide with respect to those frequencies. It's just that the numbers along the axis change. Now, in the previous section, we had mentioned describing quantitative data sets with the acronym SOCS, SOCS, but we didn't actually use it to describe any, mainly because we didn't have a graphical display of data in front of us. So to refresh, SOCS stands for shape, which we want to talk about is the distribution symmetric? Is it bell-shaped? Is it uniform? Is it skewed where it's more tilted to one side or the other? The O is outliers. Is there anything unusual? Or the data points that are far away for the others? Are there any gaps? The C is for center. What's the best representation of the center? Is it the mean? Is it the median? And then the S is spread. How much variation is there in the data? How spread out is it? Another thing that was brought up in the previous section that's worth repeating is a normal distribution. This is a distribution that's bell-shaped. It starts low, increases to a maximum, and decreases again. It's unimodal and symmetric, and it's very prominent in statistics. It gets more important as we get further into the more advanced material. Here we have another data set where in the last section we were dealing with the Best Actress Academy Award. In this data set we have the Best Actor Academy Award. We're going to use this to create a histogram and we're going to compare it to the Best Actress Academy Award. Now if you're following along in your notes, you'll see a place where you can create this histogram, but there's a few things I want to mention. So to start, we want to make sure that our axes are scaled appropriately. So if we look at our frequencies, for example, our highest frequency here is 28. Okay, so maybe make the top of that bar there 30 and then space those out appropriately so it reaches 30 at the top. Horizontal axis is going to use our class boundaries here. So it's going to go from 21 all the way up to the top here, which is 80, but we're actually going to put 81 as the last number on our histogram, and I'll explain why in a minute. We want to label our axes as well, and the height of these bars are just going to be our frequencies. So when it's done, it'll look like this. Okay, so to note the key things here, so we have bars that are these frequencies, 3, 26, 28, etc. You don't have to write the numbers above it. That's just there to help you. They normally won't be there. Along the bottom, we have our class limits. Okay, 21 for that first class, 31 starts the second class, 41. Now I mentioned we're not going to put 80 in the table over here. We're going to put 81, right? Because all these bars are the same width. They have a class width of 10. So once we get to this last bar here, we want this to have that same class width of 10. Okay, so we go 10 over from 71, we get to 81. Keep note that each of these numbers starts the next bar. So 81 is starting that bar to the right, and there's nothing in the bar to the right. Okay, we have labels. This is labeled as frequency. This is labeled as age. And then we always want a title for any graph that we make. Now we want to describe this graph, and we want to compare it to the distribution of female winners, which we have here on the right. Okay, and it's saying what can we say generally speaking about female winners versus male winners. So let's deal with that one first, and then we'll go back to describing it. So when we look at the distribution of male winners, it's starting low, it's increasing to some maximum, and then it's decreasing. So this is approximately symmetric, unimodal and approximately symmetric. Compared to females, this is really heavily weighted on the left side, and then it trails off on the right. This is called skewed. And when a distribution is skewed, it's always skewed towards the tail. The tail for this one is on the right. So this is skewed right. So their shapes are different, most notably. Okay, a skewed left distribution would have a tail to the left. Okay, so generally speaking, we can see that females win at a younger age than males do. Most females are winning in their 20s or 30s. Most males are winning in their 30s or 40s. Now let's backtrack to the original question and describe this distribution using socks. We're only using this graph on the left. We don't care about this female's graph right now. Okay, also keep a note that if we have the data and we're able to look at that table with all the numbers in it, this answer is going to be different than if we're just looking at the histogram. Because when we're looking at the histogram, we don't have all the original data. So for shape, we already discussed, it's approximately symmetric and unimodal. Outliers, doesn't appear there's any outliers from looking at that histogram. Center, this is a bit subjective at this point. We could say anything really from low 40s to probably mid 40s. Okay, any of those would be okay. And then spread, there's a number of different measures of spread that we'll learn about. We don't know them yet, so right now we're just going to use the most basic, which is the range. The range is 21 up to, but not including, 81. So it goes from 21 up to 80. Okay, we're going to take all that information and put it into a blurb of 2 or 3 sentences, and it looks like this. The distribution for the ages of Best Actor winners is unimodal and approximately symmetric. That's the shape. The center of the distribution appears to be in the low 40s. There are no apparent outliers, and winners ranged in age from 21 to 80. Okay, it needs to be written out like that and not listed just as components. We answered on this on the previous slide, but what can we say generally speaking? Comparing the distribution, the center is obviously larger for men. The shape for women is skewed to the right. Generally speaking, women win the Academy Award at younger ages than men. Now here we have another SOX question, except that in this case it's asking us to compare the two histograms. And when it's asking us to compare, we need to make sure that we use comparative language, meaning more than, less than, the same as, different than, etc. So we have the histogram on the left showing the histogram of cherry prices, and then the one on the right showing apple prices. Viewing this histogram of cherry prices, looking at the shape first, this is approximately symmetric and unimodal. Outliers, I don't see any. Center, maybe around 75. And spread goes from 60 up to, but not including, 90, so 89. Apple prices, either approximately symmetric or maybe a slight skew to the right. Again, no outliers. Center, if we're going to say a slight skew to the right, let's say it's on the upper end of this. So we'll say maybe about 65, and spread from 50 to 84. So when we write this out, the distribution for the cost of cherries is unimodal and approximately symmetric, with a center around $75 per bushel and a range between $60 and $89 per bushel. So that was for the cherries only. Also, just to note, we always want to have that approximately before symmetric if it's not exactly symmetric, which it pretty much never is with real data. Apples had more variation in their prices, ranging from $50 to $84, and a lower center of about $65 per bushel. The shape of the distribution is also unimodal, but has a slight rightward skew. This is the comparative language. Okay, when it says compare, make sure you have words like that.